We'll discuss refraction at plane surfaces in this lecture. The concept which we develop is good for any examination, board examination, JEE or NEET. Things are simple, they're not that difficult. We'll develop Snell's law and then based on Snell's law, we'll see some examples. We have an interface which divides two mediums. Let's say this is air and this is glass. It can be any pair. This is air and this is glass. And you know that when light travels from rarer to denser, it deviates from its path. So if I say that this is the incident ray, then this is the original path. Had it been air all throughout, then that's the path it would take. But you know that it's not going to happen. We draw a normal at this point. That's normal. Now when light moves from rare medium into a denser medium, it bends towards the normal. Towards the normal. This is angle of incidence I. This is angle of refraction R. Now what Snell found, he found that if you take the ratio of sine of I and sine of R, then this ratio is always a constant. Sine I upon sine R, this ratio is always a constant. If you change I, R will change such that sine I upon sine R, it always remains what? Constant. And just remember this part, I upon R, it's not constant. I upon R is not constant. What is constant? Sine I upon sine R. This constant is called refractive index of glass with respect to air. That's how you write it. Sine I upon sine R is a constant which is called what? Refractive index, which is given by mu of glass with respect to air. That means of that medium in which light rays are entering. This is that medium from where light rays are originally coming from. This refractive index, if is with respect to air, then we simply write it like this. If nothing is written over here, that means refractive index is with respect to air or vacuum. We consider air and vacuum almost equivalent. Now, this is when light ray moves from a rarer medium into a denser medium. From rarer, denser, it moves towards the normal. Whenever light moves from rarer to denser, angle I will be always greater than what? R. And this angle which you see, it will be called angle of deviation. This is the angle of deviation. What is angle of deviation in this case? You can see that this angle is I. If this is I, that means this whole angle is also I. This is I, this is R, and therefore angle of deviation is coming I minus R. Now, if something like this happens, if you say that light is moving from glass into air, what is happening this time around? You're moving from denser medium into a rarer medium. When you move from denser into rarer, that's your incident ray. This is the incident ray. Incident ray, the point where it meets with the common interface of these two medias, you will draw a normal. And then this is your angle of incidence I. You know that when light moves from denser into rarer, it moves away from the normal. This is the original path. In a light ray, it moves like this. It moves away from the normal. This angle is R. In here you can see that R is greater than what? I. This R you can see is greater than I. This is happening when light ray moves from denser into rarer medium. But now look at this figure and this figure. If you think in terms of law of reversibility, what was law of reversibility? If you change the direction of light ray, if you reverse it by 180 degrees, then it retraces its own path. Which means what? If you make this refracted ray an incident ray, then this incident ray will become what? Refracted ray. That's what is happening in this figure. If you make this incident ray, then incident ray is in glass like this. And then this incident ray becomes what? Refracted ray, which is in air. It's in air. That's how law of reversibility can be used, and that's how you can justify I greater than R. At the same time, in this figure, R greater than I. R of this figure is I of this figure. I of this figure is R of this figure. That means what? We got an interesting thing. If I use Snell's law, then refractive index of, I told you, light is entering into what? Light is entering into air. You must write air at this place. It's coming from glass, and therefore this is glass. Now how do you read it? Refractive index of air with respect to glass. Now what is this? This is sine I upon sine R. Sine I upon what? Sine R. This is always sine I upon sine R. Refractive index of air with respect to glass. Now first thing, you can see that this number should be less than 1. Why? Because of this. I is less than R. If I is less than R, then sin I is what? Less than sin R, and therefore refractive index is what? Coming less than 1. As a matter of fact, you can remember something like this. Sin I upon sin R. Whenever you go for refractive index of a rarer medium with respect to denser medium, this thing will always be what? Less than 1. And right here, you can see that since I is greater than R, this mu will be what? Greater than 1. Which means you can remember it like this. Refractive index of a denser medium with respect to a rarer medium is always greater than 1. Coming from this, I is what? Greater than R. I is greater than R, and therefore this refractive index is what? Always greater than 1. Now, let's relate this mu with this mu. As I told you, if you use law of reversibility says what? R of this case is I of this case. R of this case is I of this case. Which means what? This sin I upon sin R, it can be rearranged in this form. This sin I upon sin R can be rearranged in this form. Refractive index of air with respect to glass is what? 1 upon, look here, 1 upon what? Sin R divided by sin I, divided by sin of I. Let's add these things together. Sin R upon sin I. Now, just to make things clear, let's say this is I dash. This is R dash. If I say this is I dash, this is R dash, then this R dash is equivalent to what? I. And this I dash is equivalent to what? R of this figure. Which means this thing, which is sin R dash upon sin I dash, R dash upon I dash is basically what? This is 1 upon sin of R dash I divided by sin of I dash. I dash is what? R. That's your R. And what is the denominator? What is this denominator? Sin I upon sin R. Sin I upon sin R. Sin I upon sin R is refractive index of glass with respect to air. This is refractive index of glass with respect to air. So what we got? We got this. Refractive index of air with respect to glass is 1 upon refractive index of glass with respect to air. This also gives us what? If you say that this number is greater than 1, then automatically 1 upon will make it what? Less than 1. This is basic introduction, how Snell's law works, and then again we will develop the same ratio, the same relation with the help of speed of light. But first, note down this much. Now let's introduce speed of light in Snell's law. First thing, speed of light is represented by c. In a denser medium, speed of light is less as compared to speed of light in a rarer medium. For example, in air, speed of light is maximum, which you know as 3 into 10 to the power 8. Again, considering air is equivalent to what? Vacuum. and in glass it is considerably less. How much less? We'll see later. Why light speed decreases in denser medium? You can understand in this way. It interacts with lot many particles, lot many molecules, and due to that interaction, speed basically decreases. And we'll understand more fundamental reasoning later on. As of now, speed of light in a denser medium is always less than what? That in the rarer medium. The sin I upon sin R for this combination of air and glass is speed of light divided by speed of light. Now, if I ask you, it is one of these two, either Ca upon Cg or Cg upon Ca. One of these two is the correct one. Then I hope you can understand I is greater than R, which means sin I upon sin R is greater than 1. Refractive index of glass is with respect to air is greater than 1, and therefore this ratio should be greater than 1. Now this is a denser medium, this is rarer medium. Speed of light is less as compared to air, and therefore this ratio gives you what? Less than 1. Whereas this ratio gives you what? Greater than 1. And therefore you can see this is the correct version and that's the wrong version. Speed of light in air divided by speed of light in glass. Now, let's generalize this whole thing further. If you say that light is coming from air into a medium, let's call medium 1. Light is coming from air into what? A medium 1. That's how you will draw the path. Any medium will be always denser than what? Air, and therefore light ray will always deviate towards the normal. For this sin I upon sin R will be what? Refractive index of medium 1, refractive index of medium 1 with respect to air, which is what? Which is speed of light in air divided by speed of light in medium 1. That's what refractive index of M1 is. And as I told you that you can also simply write it like this, mu M1, or simply mu1 for us. When I say mu1, remember refractive index of medium 1 with respect to air. This is coming Ca divided by C1. When I write C1, now remember C1 is what? Speed of light in medium 1. Same argument we can use for another medium 2, and therefore let's not waste time, write down that thing directly. If I say that refractive index of medium 2 with respect to air, you can write this whole thing as simply what? Mu2, which is what? Speed of light in air divided by speed of light in medium 2. Speed of light in air divided by speed of light in medium 2. Now, look at this setup. Suppose you replace air with medium 1 and you replace glass with medium 2. As of now, just assume that medium 2 is denser than medium 1 so that we can still keep this figure. Light ray bends towards the normal, but later on you will see that it doesn't matter. Maths will take care of this automatically. Now, this is medium 1 and this is medium 2. And if this is medium 1 and medium 2, then sin I upon sin R is what? Refractive index of glass with respect to air. This thing now becomes what? This thing now becomes what? Refractive index of medium 2 with respect to medium 1. Refractive index of medium 2. Glass is 2, air is 1. Which is basically what? C air. What is air? This thing. And therefore C1 divided by C2. Sin I upon sin R. You will write it separately. मैंने इसलिए mention कर दिया so that you can relate it with this figure. Sin I upon sin R. You will go directly for mu 2 1. Refractive index of 2 with respect to 1, which is from this argument C1 upon C2. Now this C1 upon C2 can be rearranged in this form. C A upon C2 whole divided by C A upon C1. CA, speed of light in air is cancelled. This C1 moves to the numerator, denominator, and you get what? C1 upon C2. Now what is CA upon C2? What is CA upon C2? Mu 2. And what is CA upon C1? CA upon C1 is what? Mu 1, which means this relation is now refractive index of 2 divided by refractive index of 1. What do you got? Refractive index of medium 2 with respect to 1 is refractive index of medium 2 with respect to air. When there is nothing here, it means air, divided by refractive index of medium 1 with respect to air. Now if you look at this part, how can you remember this whole thing in a very easy manner? Look at this combination C1 upon C2, which is ultimately is equal to what? Mu 2 upon mu 1. That is giving you this. This is giving you this relation. C1 upon C2 is what? Mu 2 divided by mu 1. And instead of remembering this way, if you look at this relation, it is like this. C1 into mu 1 is C2 into mu 2. What is happening? Speed of light in medium 1 multiplied by refractive index of that medium with respect to air. This thing is always a constant. Why? Because it's basically nothing but speed of light in air only. If you multiply C with mu of that medium, you basically get what? Speed of light. C2 into mu 2 is what? CA. C1 into mu 1 is what? CA. But it's easy to remember this. What is the statement which you got finally? Speed of light in any medium multiplied by refractive index of that medium. This product is always speed of light in air. For us, this product is always a constant. Which means what? If this is C1 upon C2, then it cannot be mu 1 upon mu 2. It should be always what? Mu 2 divided by mu 1. This C1 upon C2, this concept, how do you say that this ratio is C1 upon C2? We'll learn this thing in wave optics. As of now, in ray optics, you don't have to worry about it. Simply remember C1 upon C2. At times, people get confused between CA upon CG or CG upon CA or C1 upon C2 or C2 upon C1. Then for that times, remember this trick. Note down this part. So we have developed so far this thing, refractive index of medium 2 with respect to 1 is C1 upon C2, which is mu2 upon mu1. You can see from this C1 upon C2, you can write it as 1 upon C2 upon C1. What is this? 1 upon, what is C2 upon C1? Refractive index of 1 with respect to 2, which is nothing but law of reversibility. We had seen this thing earlier. And then speed of light in a medium, refractive index of that medium, this product is always a constant. It will help you in remembering this. This is C1 upon C2, this is mu2 upon mu1. Now, look here. Suppose they give you questions like this. Refractive index of A with respect to B. A can be anything, it's not here. Refractive index of A with respect to B is 3. Refractive index of C with respect to B is 4. Question is, find out refractive index of C with respect to A. Whatever we have done so far, you can expect questions like this. At this stage, pause the video, take 1 minute time, and then get the solution. Now, you need to find refractive index of medium C with respect to medium A. What is this? You simply wrote it as mu of C divided by mu of A. This is mu C upon mu A. What is this? This is mu C upon mu B. What is this? This is mu A upon mu B. We have the idea of mu A upon mu B, we have the idea of mu C upon mu B, and I'm asking you, what is mu C upon mu A? What should you do? If you divide from this part, then mu B and mu B is cancelled. It's like this. What is this whole thing? This whole thing is what? Mu C upon mu B whole divided by mu A divided by mu B. B and B cancel and you got what? Mu C upon mu A. This and this, these numbers are already known. This is what? 4 divided by 3. That's how you can use these relations for finding values like these. Then you can also ask a question like this. Arrange refractive indexes and corresponding speed of light in that particular medium in the increasing order. In the increasing order means mu A, mu B, mu C, CA, CB, CC. You have to arrange these things in what? Increasing order. Again, note down this much, pause the video, and then find out the relation which I'm asking you. Then come back and see the solution. We have to arrange mu in increasing order, C in increasing order. First, let's talk about mu. Look here. Mu A upon mu B is what? 3. 3 means something which is greater than 1. Just mu A upon mu B, this mu A upon mu B is basically what? Greater than 1. This relation gives you mu A greater than mu B, because this is 3. Same here. This ratio is also what? Greater than 1. And therefore this thing gives you mu C greater than mu B. Mu C greater than mu B. Either you can fit C here. If you fit C here, then it satisfies this. If you fit C here, again it satisfies this. Now where should I fit this mu C? For that, we'll go with this part. Mu C upon mu A is what? 4 upon 3, which is again a number greater than 1. If this number is greater than 1, that means from here you got what? Mu C greater than mu A. Mu C is greater than what? Mu A. This, and this, they all give you this relation. Mu B is the least, then comes mu A, and then comes mu C. That's the increasing order of their refractive indexes. Now, note down this, and hopefully you can find same thing with speed of light. Pause the video, come back and see the solution. Look at the solution. Solution is already here. C, 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 A, C, B. Just reverse the sequence. Why? Because of this. Because of this. This is mu2 upon mu1. This is C1 upon C2. Because of this, Cm into mu m is what? Constant. If you are increasing mu, that means you are decreasing what? C. This is the maximum mu, and therefore speed of light in this medium should be least. In just one line, you can move from this position to this position. Very interesting small example. Just remember this profile. At the same time, you can also remember something like this. We could have answered this question using a chain rule. What is the chain rule? Refractive index of B with respect to A multiplied by refractive index of C with respect to B multiplied by refractive index of A with respect to C is always 1. That of B with respect to A, that of C with respect to B, that of A with respect to C, this thing is always what? 1. Something like this. Let's write down A, B, C. You can always add D, E, F, anything. Suppose you are moving in this direction. It has nothing to do with direction. You can take any direction. Now, refractive index of B with respect to A. Refractive index of C with respect to B. Refractive index of A with respect to C. Just follow this sequence. You can reverse the direction also, it doesn't matter. Of C with respect to A, of B with respect to A, of A with respect to B. This product for any number A, B, C, D, E, F will be always what? 1. And the reason is what? Very easy. This A is on the left side, this A is on the right side. Which means what? Which means what? If 1 is on the left side, then it is in the denominator. 2 is on the right side, numerator. Which means everything A will be in the denominator as well as in the numerator. Numerator, denominator, denominator, numerator. What is this first thing? First thing is mu B upon mu A multiplied by mu C upon mu B multiplied by mu A upon mu C. You can see that this thing is coming what? 1. A, B, B, C, C cancel. You could have answered this question with the help of this approach also. How can you answer? Let's see. We have been given what? Refractive index of A with respect to B, which is what? 3. But this is what? Refractive index of B with respect to A, which means this thing is 1 upon 3. Coming from this, coming from this. Then refractive index of C with respect to B. Refractive index of C with respect to B is what? 4. Multiply this thing with 4. Multiplied by what? Question says find out refractive index of C with respect to A. But this is of A with respect to C, which makes it what? 1 upon refractive index of C with respect to A. The whole thing is what? 1. Move this over here and you get your answer as 4 upon 3. But I will advise you that always follow this technique. It's much easier. You can simply see the relation and you can find out what to do. You need to multiply or you need to divide. That thing you can easily see. We have to find mu C upon mu A. You can see mu B and mu B is what? Cancel. Note down this much. Now look at this example. We have multiple mediums present. Say this is medium 1, medium 2, medium 3, medium 4, and so on. Now, this is the incident ray. This is the incident ray, that's the normal which you draw at this point. Let's say refractive index of 2 is greater than that of 1. That means this is a denser medium, this is a rarer medium. Although it doesn't matter for the concept which we are going to develop. Then light bends towards the normal like this. This is I1. This is R1. What is Snell's law? Sine I1 upon sine R1. Sine I upon sine R is refractive index of medium 2 with respect to 1. Medium in which light enters. The medium from which light enters into the second medium. This whole thing you know is what? Mu 2 divided by mu 1. Sine I1 upon sine R1. Now, when light meets this next medium at this interface, again you will draw a normal. That's a normal. And let's say this medium is rarer as compared to this. Just so that we can make a neat and nice figure. Otherwise, conceptually it doesn't matter. And if you say that this is rarer as compared to this, then light ray is moving like this. It moves like this. When it moves like this is your new angle of incidence I2. Angle of incidence is taken from the normal of the incident ray. This ray is refracted ray for 1 and 2. The same ray is incident ray for 2 and 3. And we'll be using this point. This is I2. This becomes what? R2. Now look. If I say that all these interfaces are parallel. That means this R1, this R1 is nothing but alternate angle I2. If these two interfaces are parallel, that means these two normals, they are also what? Parallel. If they are parallel, that means R1 is what? I2. If R1 is I2, then first thing, look here. This relation now can be written as sine I1 upon sine. Let's replace R1 with what? I2, which is coming mu2 upon mu1. Now look at this form, cross multiply these things and you get what? Mu1 sine I1 is mu2 sine I2. Mu1 sine I1 is what? Mu2 sine I2. We'll come back for this, but now look here. When light moves from M3 to M4, again draw the normal, that's your normal, and then whatever be the refractive index type, let's say it's denser as compared to this, then light moves like this. When it moves like this, what is this? Angle of incidence. This is angle of incidence, call it I3. This is angle of refraction, call it R3. But again, look at the argument. These two, they are parallel, which means these two normal, they are also what? Parallel. If they are parallel, that means I3 and R2, they are same. I3 is nothing but R2. I3 is nothing but R2, which gives us this. For refraction from 2 to 3, this is for refraction from 1 to 2. 1 to 2. For 2 to 3, you will be using Snell's law in this form. Sine I2 upon sine R2 is refractive index of 3 with respect to 2, which is mu3 divided by mu2. Now this sine I2, what happened? You're discussing refractive index when light moves from 2 into 3. 2 to 3. 2 to 3. This is incident ray, this is refracted ray. Snell's law is what? Sine I upon sine R. Sine I2 upon sine R2. But R2 is nothing but I3, and therefore you can replace this R2 with what? I3. Right side is mu3 upon mu2. Again cross multiply and you get what? You get this mu2 times sine I2 is mu3 multiplied by sine of I3. Now this is mu2 sine I2 equals to mu3 sine I3. This is mu2 sine I2 equals to mu1 sine I1, which means from all these three you're getting something like this. Mu1 sine I1 is mu2 sine I2 is mu3 sine I3, and you can continue this for this fourth medium also. This is I3, this is R3. This R3 for the next part will become what? I4. Just like this. Just like this. And therefore, we will use a simple trick. If you are in medium 1, then your angle is what? I. If you are in medium 2, then your angle is what? I2. This is I2, angle of incidence. This is also I2, which is angle of refraction. Angle of refraction for 1 to 2. Angle of incidence for 2 to 3. When light is in medium 3, we'll use I3. This R2 is basically what? I3. This R2 is angle of refraction for 2 to 3. But this is angle of incidence for 3 to 4. Once you do this, you get this relation, which ultimately gives you something like this. Refractive index of a medium multiplied by sine of angle of incidence in that medium. Angle of incidence in that medium. This product is always a constant. This product is always a constant provided all these interfaces are parallel. You can see that if these interfaces are not parallel, then these normals, they will also not be parallel, and then we cannot use argument like this. We cannot use argument like this. You can write this statement along with this condition that this relation is valid for any type of different layered media where their interfaces are all parallel. A little while ago we got this relation mu of a medium, c of a medium, which was constant. It has nothing to do with this type of condition. Refractive index of a medium, speed of light in that medium is always a constant. Why? Because this constant is nothing but speed of light in air. But this condition, it requires that all surfaces must be parallel. Now, what is the advantage of this whole part? What is the advantage of this whole part? Let's see this thing with the help of one example. Example is what? We are given a situation like this, that this is air, this is water, this is glass. Air, water, glass. Light is coming at an angle of 30 degrees. Angle with the normal, this incident ray makes is what? 30 degrees. Then it enters into what? Water. You again draw a normal. Then it enters into what? Glass. Question is, what is the angle which light ray makes with this normal? Air to water to glass. All the faces, all the interfaces, they are parallel, and our aim is to find this theta. Let's call it what? Theta, and we need to find this theta. Just remember this information. Refractive index of glass with respect to air is 3/2. Refractive index of water with respect to air is 4/3. Standard data, you can remember this. Refractive index of glass is what? 3/2. Refractive index of water is what? 4/3. And question says that find out this theta. Shouldn't take more than 15 seconds. If you wish, you can pause the video and go for it. Then come back and see the solution. Now, normally people, what they do, they transfer this light from this to this and then from this to this. They will go for this angle, they will find this angle, and then ultimately they will arrive at this angle. Instead, what we can do is, we have developed this relation. Now this relation says what? You can use a trick like this. The trick is, refractive index of air multiplied by sine of angle in that medium. What is that? 30. Refractive index of the medium multiplied by sine of angle in that medium, which is what? 30. This is 30. Then what? Look here. Refractive index of directly move from water to what? Glass. You don't have to worry about water because they are always what? Same. From this, we are moving directly to this. This is refractive index of glass. Refractive index of glass multiplied by sine of theta. Sine of theta. Refractive index of air is what? 1. Because refractive index of air with respect to air, it will be simply what? Mu A upon mu A. Refractive index of air with respect to air will be mu A upon mu A, which is what? 1. Or I and R, they both will be same, and therefore sin I upon sin R will fetch you 1. Hopefully you can see question is done. This is 1. Sin 30 is what? 1 by 2. Mu G, it's given 3 by 2 multiplied by sine of theta. 2 and 2 cancelled, and you got sine theta as 2 by 3, or theta as sine inverse 2 by 3. This is the advantage of this relation. Remember this relation with the condition I told you. Surfaces should be parallel. Note down everything.